can get started. Okay. Okay, so hello everyone. Today we'll talk about let me just right here. Today I want to take a challenge. I will try not to look at my notes and give you this section talk. So what we want to talk about today is called strong or you can say it is strongly connected, whatever, of directed graph. And then after talking about the strong connectivity of a directed graph, I will lead you guys to review DFS and BFS, which you have already learned in your lecture. Did you just learn it yesterday? For DFS and BFS. Okay, so first I want to spend around 10 to 15 minutes to talk about the first topic, because this is much easier than the second one. But when I talk about the strong connectivity of direct graph, I will assume that you know what is DFS and BFS. But if you don't remember the details of DFS and BFS, it doesn't matter at all. I just introduced the way to detect if a graph is strongly connected or not. But it is based on DFS and BFS, but you just need to know what are they. So let's first tell the definition. G and A is, so I will write SC to be strongly connected, okay? G and A is SC if, who can tell me the definition of it? Has Dr. Costello tell you the definition of strongly connected? Okay, so so a graph G, but of course we are talking about directed graph today. So a directed graph G is strongly connected if for any I, J in a node set. But of course we should assume IJ are different, otherwise it is trivial. So for any IJ in a node set, there exists at least one path from I to J, and also there exists at least one path from J to I. So this means strongly connected. So what is the application of a strong connectivity of a directed graph? So think about this problem. Suppose we are talking about the roads in a city. And you know that for the roads in a city, some of them are one ways, which means that, say from position I to position J, one way means that you can only go from I to J, but you cannot do the reverse. So when we are talking about the roads and also the size of a city, we want to know that if it is strongly connected or not. That's to say, if you can go from any place to any other place. So this is the application of strong connectivity. This is the definition. Okay, so next, I want to introduce the way to detect if a graph is strongly connected or not. So first, I want to ask you, in the lecture, Dr. Costello introduced the search algorithms, which means DFS or BFS. Can you tell me what do they do? That's to say, I tell you that this is a DFS. Oh, take a seat, please. Can anybody tell me what does DFS or BFS do? What do they do?
DFS is like a key system, so the first one is the first one, right? Or
let's think about in this way. What is the input of DFS or BFS? Input. So we should input a directed graph G, right? Oh, by the way, we are talking about directed graph today. So regardless of undirected graph. So first we need to input the graph G, right? What else? What are the, is there any other input? we need a starting point S, right? That's to say, I give you a network, and I also need to tell you a starting point S. And then, what do they output? DFS and BFS tells you what are the points, what are the nodes that you can reach starting from S. So let's just use a notation. I didn't see this notation on textbook, but for our convenience today, I will use NS. This means that V such that V is a node, and there exists at least one path from S to V. So that's to say NS is the set of nodes that are accessible from S in this graph G. So this is what the search algorithms do, DFS or BFS. It returns the set of all the nodes that are accessible from your starting point S. Okay, so now my question is, by conducting DFS or BFS on our graph, we can know that what are the nodes that are accessible from S. So my question is, how do you know I define a new set, which is called NS prime. So the definition of NS prime is V, such that V is a node, and there exists at least one path from V to S. This is my question. Can anybody tell me what do you think? This is the output of DFS or BFS. But now I want to know NS prime, which is from where that you can go to to the point S. So now S becomes the destination rather than starting point. Any idea? So I'll give you a hint. The hint is that you just do some modification to your graph, or say to this network. Okay, no answers. So the solution is that, so in order to obtain this NS prime, what you need to do is to reverse the arcs in this G. So what does it mean? It means that now we obtain G prime, which has the same node set, but the arc set is different. And the arc set is that we have the arc from node J to node I, such that there is an arc from I to J in the original arc set. This means that, so suppose originally you have this graph with 3 nodes, and there's an arc from 1 to 2 and 1 to 3. So if you reverse it, I mean, it becomes in this way. So now I tell you that we need to reverse the arcs in G. What's our next step to obtain this NS prime? Use DFS or BFS. How can you obtain this NS prime? Anybody has an idea? Okay, so the next step is, okay, so from this right here, we do DFS/BFS on G prime with starting point S. Why? That's to say, so suppose this is our G prime. This is your S. And suppose in G prime, you conduct DFS or BFS. And suppose you can reach a point, say, T. That's to say, in G prime, you can go from S to T. Then what does it mean by in G? You just reverse every arc on this path. That's to say, in G, there exists at least one path from T to S. So that's to say, first you reverse all the arcs in G and you obtain G prime. And then you do DFS or BFS again, but on G prime with the starting point S. So in this way, you can obtain your NS prime. The definition of NS prime is written there. That's to say, from NS prime describes all the points such that you start from them and you can reach your starting point, reach the point S. Okay, so now that we have NS and NS prime, is it enough to determine that a graph is strongly connected or not? Where should I write? Okay. So we call it a proposition, whatever. So you know that in a paper, theorem is more important than a lemma, and a lemma is more important than a proposition. So let's just call it a proposition. So the proposition is that a graph G is strongly connected if and only if NS and NS prime is just the node set for any S in the node set. So look at this. Why? Oh, by the way, so for those who came later, this means strongly connected. So a graph is strongly connected means that you can go from any node to any other node. So I claim that our graph G is strongly connected if and only if the set of nodes that you can go from S is equal to just all the nodes. And also the nodes that you can go to S is also this node set. Is this clear? So we just do a very simple proof. So for this direction, it's very easy, right? G is strongly connected means that for any S and any T, there is a path from S to T. And also there's a path from T to S. So NS and NS prime must be equal to the set of all the nodes. And in this direction, that's to say for any, say I, J in the node set, you can always go from I to S. Why? Because NS prime is N. And then you can go from S to J, because NS equals to N. So that's to say, this is a very brief proof to this proposition. So that's to say, when we want to determine if a graph is strongly connected or not, it is equivalent to say that we need to check whether NS equals to NS prime equals to N for any S in N. However, here's the trick. We don't need to check for every node S. We just need to check one node. Why? Because suppose now you have already checked the node. You have checked the node 1. You have checked the node 1. And we know that N1 equals to N1 prime. This equals to N. Can we say that this graph is already strongly connected? Right? From any node, you go to from any node I, you just go to node 1. And from node 1, you go to node J. And vice versa. However, if you just randomly check a node, suppose now you have checked node 1, and you find that, say, N1 is a proper subset of N, then this is not strongly connected, right? Because from node 1, there exists at least one node that you cannot go from 1. So this must not be a strongly connected graph. Okay, so let's say it again. So if we want to determine a graph G is strongly connected or not, what we need to do is to first, we do DFS or BFS starting from S on G. What do we obtain? We obtain NS. And then we reverse the arcs of this graph. And we do DFS or BFS again, starting from S, and we obtain NS prime. And then we check if NS equals to NS prime equals the set of all the nodes. If it is true, then this graph G is strongly connected. Otherwise, it is not strongly connected. Is that clear? Okay, makes sense. That's the first part of today's section talk. Then I will lead you guys to review the DFS and BFS that you learned in the lecture yesterday. So as I have said before, DFS and BFS returns all the nodes that are accessible from S. So what's the main idea of DFS and BFS? This DFS means that it is depth first search. And this means that it is breadth first search. So if you want to express it in a network, let's just consider this very simple one. So for DFS, the sequence, the order is like you go through this way until you reach the end. This is the depth. And then you do this way, and then you do it in this way. This is the depth. But if you do BFS, so what does a BFS do? What you do is you first do this layer. Here I call layer. A layer means that it's just like cutting an onion, right? So in an onion, you see there are layers. First, you cut this layer, and then in this manner, this is called the breadth. I think I spelled it correctly, right? Okay, because it is very, very easy to misspell it to the word breadth. Okay. So so for at least from this, this is the brief idea of DFS and BFS. And I double checked the lecture slides, and I see that Dr. Costello introduced the way to use a list to implement the DFS and BFS, right? In an iterative manner. So can everybody just pull out the lecture slides? It is called search algorithms, right? That I remember you learned it yesterday. So let's just write it out. Function search. But now the search can either mean a DFS or BFS. Okay. So what does it do? So we mark every node as unvisited. let's don't write it in this way. So actually, in the actual implementation, first you want to mark that every node is node visited. What we do is we introduce a hash map. It is called visited. B false for V in the node set. In Python, it is called a dictionary, but in general, it is a hash map. That's to say, the key is the node, and the value is false, means that we have not visited yet. And actually, when you are writing in Python, there should be a curly bracket. When you are writing in Python, if you want to initialize a list or initialize a dictionary, you can just write it this way: V false for V in N. This is called list comprehension. Okay. So I want to mark every node as unvisited. What's the next step? What should we do? Just to recall what you have learned in class. Right, of course. Oh, yeah, by the way, sorry, I didn't write it. This should be the input. We have, you need to input a graph G and the starting point S, right? So now you have already marked every node as unvisited. And then we need to say that, okay, we initialize a list and we put S into this list, right? This is what you learn. And then you mark visited as is equals to true. Sorry, I need to refer to her lecture slides. Search results. Right. So if you look at this page in your lecture slides, the first step is to unmark all the nodes in N. This is what I do here. And we have a list, and also pred s equals to 0. So what does this mean? This means this pred means that it is a predecessor. So if you look at this DFS, you will find that after DFS, you can identify a tree in this graph. So DFS actually it returns you a tree. And in a tree, you know that, so suppose this is an arc in a tree. We call, say, I and J. So I is J's predecessor. I is J's predecessor. And J is I's successor. This is a definition. So pred s means 0, means that S is just the root node because it is a tree. And we want DFS to, the search algorithm to help us to return a tree such that we know the predecessor of each and the successor of each node. So pred s equals to 0. And also we need to order s equals to 1. It means that, so order, what does order do? Order is to track the visiting order of nodes. That's to say, in the search algorithm, in the first step, you visited what? And then in the second step, you visit the what. So this order means that I want to track the visiting order of the nodes. Okay, now we enter a while loop. While the list is not empty, we select node I from list. Okay, so we see that in the lecture, I think Dr. Costello has already told you that if for DFS, the list is a stack, while for BFS, the list is a queue. You have not learned data structure and algorithm before. I can tell you that. So a stack is a data structure that is, it is a data structure, which means that you can put your data points into it. A data structure is like a container. So a stack is first in, last out. That's to say you see that first we put a node S into this stack. So this stack is like you put it inside it, and it should be the last that you take it out. It is something like this. First in, last out, right? Or say last in, first out. This is for stack. And for queue, it is first in, first out. So it is like it is like a queue in reality. So you enter here and you get out here. It is a first in, first out data structure. So here I say select node I from list. If it is a stack, you take the top element. If it is a queue, say this is in, this is out. Then for a queue, you take the leftmost element, first in, first out. Okay, so we select node I from the list. If next we want to check if node I is incident to admissible arc ij. What does it mean? What is the definition of an admissible arc? What is an admissible arc? Here I want to say ij is admissible. So first it should be an arc. If there's no arc from I to j, then this makes no sense. So ij arc is admissible if j you are at node I now, and j is not visited. So ij is admissible means that now you are at node I, and you see that you can go from node I to node j, and node j is not visited yet. So now ij is admissible. So you use an if statement. If node I is incident to admissible arc ij, then what you do is to then on the lecture slide it said mark node j. It means that you need to say visited j equals to 2, right? Because now you go from node I and you see node I is already visited because you are currently at node I. And you see that node j is incident to node I, and node j is not yet visited. Then you go to node j, and now you have already visited node j. So visited j equals to 2. You have already marked it. And we record that the predecessor of j is I. Why? Because you go from node I to node j. Then node j's predecessor must be node I, right? And the order j just it is just equal to I think I need to add one more variable here. So here we also need to add a variable, let's just say clock equals to 1. Clock means that it tracks the order, saying now clock equals to 1, then order S. Here the order S should just be equal to clock. Sorry, I need to make a modification here. So clock should be added here before the order of S. So clock means that the order that you have traveled through these vertices. And then the order of S is just the clock. And then you have go from node I to node J. Then what you need to do is to write clock. This means that you add clock by 1. So suppose in the first iteration, clock equals to 1. Then clock plus plus means that clock, the variable clock now equals to 2. And the order of J now equals to clock. That's to say, the order that we have visited node J is equal to this clock. So say clock, initially it is 1. And in the first iteration, it becomes 2. Then the order of J is just equal to 2. Otherwise, else we delete I from list. Sorry, it's a little bit, we have run out of space. So that's to say, if now from node I, you check all the node J that is incident to node I, but you find that all the node J that is incident to node I have already been visited. So that's to say, now at I, you have already reached the end, right? So you need to delete I from the list. I understand that this may be a little bit confusing now. So let's just look at the graph and see what happens. So suppose wait a second, let me pull out the example that Dr. Costello had told me. Okay, so let's just look at this example. So we have node 0, 1, 2, 3, 4, and 5. And these are the arcs. And say now I want to do a DFS starting from node 0. And we have a stack, say the stack now it contains 0. Then according to this algorithm, what are we doing? So we see that, okay, so we start from 0, and then we see that 0 is incident to 1, and 1 is, so 0 is visited. We see that 0 is incident to 1, and 1 is not visited. So what do we do? We need to, so now we go to node 1, right? So node 1 is visited. And we see that node 1's predecessor is node 0. So what do we do is that, so node 0 has order, what's the order? What does the order start? Okay, order 1. It means that in the first node that we visit is node 0. And then we reach node 1. And node 1's predecessor is node 0. So this is the first arc that we have traveled. And node 1 has order 2. Then what do? We also put node 1 into the stack, right? So now what does the stack look like? The stack is like 0, 1. And then what's our next step? So we are now in the while loop, and we select the top node from this stack. So top node is node 1. What do? We check that, okay, so node 1 is incident to 2 and 3, right? So we just choose, so we choose node 2. So there's so we go from node 1 to node 2, means that node 1 is node 2's predecessor. And node 2 should have order 3 because we go from node 1 to node 2, and node 1 has order 2. Okay, so next our stack looks like 0, 1, 2. And then we see that, okay, so we take node 2 out, and we see that, okay, node 2 is incident to node 3. So 2 is 3's predecessor, and node 3 has order 4. And also in this manner, our stack is just 0, 1, 2, 3. Then we do the similar thing. Okay, so we see that 3 is incident to 4, and 4 is not visited yet. So now our stack looks like 0, 1, 2, 3, 4. And what is the order of visiting node 4? It is 5. And then we see that we can also go from node 4 to node 5. So the stack now becomes 0, 1, 2, 3, 4, 5. Now, what happens? At node 5, we have visited, but we see that node 5 is not incident to any unvisited node, right? So what we do next is to backtrack, right? Remember this word, backtrack. So that's to say, now, still in the while loop, because the while list is not empty. So we see that this list is not empty now. So what we do is that, is node 5 incident to any admissible arc? No. So we need to delete 5 from the stack. We just pop out. And just in this manner, we see that we can pop out all the elements in this stack, and we're done. So what do we obtain? Actually, we obtain a tree, right? This is a tree. For those arcs in red, this is a tree. Okay. So this means DFS. And BFS, you can do it in a similar manner. But remember that in a BFS, you replace this stack by a queue, and then every time you add from the end, and every time you pop out an element, you check the first one, right? This is the one introduced in textbook. However, I find that it is different from what I learned in undergrad. Yes, last night I discussed this question with Dr. Costello, because this is the code that this is the pseudocode that was written on the textbook and also on your lecture slides. But at first I saw that it looks wrong, because it is different from what I learned in undergrad and different from what I used to implement DFS or BFS. So now I want to introduce an alternative way to use a stack to implement the DFS or BFS. Okay. So the difference is mainly here. All the same above, but now when we are checking while list is not empty, we just need to say let equals to pop. So what does a pop mean? I need to explain here, because I know that you. I remember last week asked you whether you have already learned data structure and algorithm, and you said no. You guys said no. So what does a pop do? It is a terminology in data structure. So for a stack or queue, if you pop this stack or queue, pop means that you remove the top element and return it. So pop is a function. It means that you remove the top element and then you return it. So here I write U equals to pop list. What does it mean? It means that suppose this is a stack. This is a stack. I remove the top element, and the top element is U because I have already returned it. Remember what does the return mean in a function? Return is the function's output. So first you pop this list. You pop this list and you obtain U. Now, starting from U, what is the next step? We use a for loop for all V such that U, V is an arc. That's to say, so now you have already popped this top element from this stack. And then you see that what are the nodes that are incident to this node U. You check them. Let's just name it as V, okay? So if V is already visited, pass. That's to say, from now you are at node U, and you see that, okay, I'm incident to node V, but node V is already visited. Then I don't go there, right? Because it is already visited, so pass. Else, that's to say, if V is visited, what should we do? We need to mark visited V as true, right? That's to say, we have already. So now we have already got. So now we get to node V, and we mark it as true. And what should we do? What should we do next? We need to push V into the stack, into the list. So it means that from node V, from node U, you arrived at node V, right? And then you mark it as visited, and you push it into the list. Right. So I need to think of how to explain it to you guys. Right, so why do we need to push this node V into the stack? It means that next time if we want to pop it out, we pop it out. And then we check all the nodes that are incident to this node V, right? So in this manner, we can do a DFS, and also if you change this list into a stack, into a queue, then you can do a BFS. Is it kind of confusing? I think so. Okay. But anyway, I see that we still have 5 minutes. I want to introduce an easier method easier to understand method in terms of the implementation of DFS, which I really like. what I want to introduce is that implement DFS by recursion. I think this is easier to understand, and this is not covered in your lecture. So what does it mean? Have you ever learned recursion in any programming class? Recursion. Okay, so recursion, let me write it down. Actually, I introduced this in my first section. So we first introduce a function explore. We explore the node V. What do? We mark visited V equals to true. So that's to say we are now exploring node V, and node V is visited. And then for each for each V, U in the arc, if not visited, that's to say if node U is not visited, we just call explore U. Why is it a recursion? You see I explore here, and also I explore here. So this is a recursion. That's to say, now you are at node V, and you see that it is incident to U1 and say U2, and both of them are not visited. Then you call explore. You see that this is a for loop, and you first explore U1. And after you explore U1, and also because it is a recursive function, you have also explored the successors of U1. And then in the second iteration of this for loop, you explore U2. And because this is a recursive function, when you explore U2, you should also explore, you have also explored all the successors of U2. So in this manner, it is like you go along this direction and you visit all these successors of U1. And then in the second iteration, you explore U2 and also explore all the successors of U2. This makes sense, right? I think this is much easier to understand. Okay. Then what do we do DFS? If you can understand what does explore do, then it is much easier to understand what DFS do. So DFS, first we, of course, as a tradition, we need to mark every node as unvisited for V in the node set. All the nodes are unvisited. And then for V in the node set, as you say, we traverse every node in the node set. If not visited V, that's to say if node V is not visited yet, what do we do? Well, very easy. We just explore V. Well done. This is much easier than the implementation in your lecture slides. So an intuitive way to understand this is like, so suppose your graph has two connected components. These two connected components are isolated to each other. So first, you see that you mark every node as unvisited. And then say you start from this vertex to visit. Okay, so you visit. You have already visited all this part. And then you see that this node is not visited yet. So you start from this one and do it again. You have visited all these parts. And let me say it again. So explore means that you explore this node. And for all the nodes that are not visited and are adjacent to this node, you not only visit this node, but also nodes that are accessible from this node. And then you visit this node and also the nodes that are accessible from this node. So this means depth first search. This is much easier to understand. Okay, I think this is all of today's section. If you don't understand the stack or queue implementation, please come to ask. I know that it is not easy to understand at the beginning, at the beginning if you have no basis for data structure and algorithm. Okay,